Good morning, everyone. Welcome to this series of webinars organized by IEMAP project to be held today and tomorrow from 9:30 onward. The IEMAP project has created a distributed platform consisting of data management portal, an HPC supercomputer infrastructure, and a series of computational and experimental labs working together, distributed from the south and to north of Italy. The purpose of these webinars is to provide a didactic in a didactic mode and for dissemination and for presentation of the laboratories involved in this project and the technologies, the new technologies that have been developed during the project. Because this IEMAP platform is an open platform. It will be an open platform and open to new laboratories, industry, if no. So as you can see in the first slide, so this is a series of webinars for labs and technologies for the accelerated design of materials for energy. And hopefully we will explain you how, where, and why you can get involved in the IEMAP services and infrastructure. This is the rich agenda for today and tomorrow. We will present the platform. We will present the laboratories materials for photovoltaics, materials for batteries, and materials for electrolysis. These are the first three use cases of this distributed IEMAP platform. And the aim is to generate data in these use cases to be processed by the computational infrastructure to accelerate the discovery of materials. This is so the IEMAP is constituted by a cross-cutting computational laboratory, and then laboratories for electrochemical storage, for low temperature and high temperature electrolytes, and the photovoltaics. And as you can see, the main research institutions in Italy are involved, and the labs are distributed from south to north of Italy. The idea is to connect all the labs with a large databases for materials in order to store all the information and the new results from the research available for new research, for new involvement of new laboratories and industries. And this can be done in a circular way in order to accelerate the discovery and the study of these materials. Essentially, the infrastructure has a data generation layer that is constituted by all the labs. The labs clean the data, so this is a local data curation. Then the data are moved to the data management, the central data management and storage. This is a large data space that will increase in the following years. And then there is the upper layer devoted to the analysis and visualization of this data to discover new properties, new information, to give back directions to the labs. So this is everything from my side. I stop sharing my screen. I see Sergio Ferlito, the first speaker, connected, so I would give him the floor. Sergio, can you?
Hi everyone. I briefly introduce myself. I'm a researcher working at ENEA, located at South Italy, Ottica near Naples. And I'm currently involved in the IEMAP project. I share my screen to start the presentation. Wait only a minute. If you can give me feedback if you are able to see my screen.
No.
I don't know why this was missed. A few minutes, I try again.
Yeah. We see
Okay.
your desktop.
You should see my screen now. My first talk is regarding the general platform. You should see my first slide. This talk, it's a brief talk, about 20 minutes, about the IEMAP front-end architecture. It's a kind of walkthrough about the front-end, let's say the web interface of the platform, and the REST API or Python module that allow the user to connect programmatically to the platform. The agenda for today is articulated in this way. I show a overview of the platform with some details regarding the general architecture of the platform itself. Then I briefly introduce what's the meaning, what REST API stands for. Then a brief walkthrough regarding the front end. When I say front end, I essentially talking about the website, and it's one of the methods that the user is at its disposal to connect to the platform itself. I then briefly introduce the Python model. I developed a model in Python that is publicly available that allow to connect to the infrastructure and eventually include these facilities in user workflow. Then I'll briefly talk about the tasks that are yet to complete. So this is the general architecture. This is the website. The URL of the website is https://iemap.enea.it. If you try to reach this page, you will be presented with this kind of interface. We have a button on the left that allow to see the other contents of the page. This type or some elements of the website are freely available, publicly available, in the sense that every user without any registration can access the website. Other parts of the website are protected. This means that the user has to activate an account. On the top right, you can find two buttons, one to log in if you already have an account activated, or sign up to fill in a form to activate an account on the website. The other two pages are related to the other side of the platform. The website is the commonly used interface from users that are not skilled in programming, while to access data and all the facilities of the platform, you can use the REST API. In the following slide, I will briefly explain what this stands for. As you can see, the URL is quite similar. The difference is that it contains additional terms /REST, /API, /v1, /health. This is only one example. The main difference is that here you have a web interface, so many elements that display content in a user-friendly manner. While using the REST API, the response is stored as JSON. JSON stands for JavaScript Object Notation. It is this kind of notation where we have curly braces encapsulated key value pairs. Here on the bottom, you can find the URL for the documentation of the REST API, where it's explained how to interact with the REST API. It should be quite user-friendly. One note about this is the presence of the lock in some endpoint. Endpoint are so-called the specific URL that the user can interact with. And the lock stands for protected endpoint. This means that the user has to be first registered on the website. After registration, he gets back a JSON web token. It's a kind of passport that when user has to interact with the REST API for a protected endpoint, has to present to the website to be granted access. This is the general architecture. Only a few notes. This kind of platform was developed with the back-end, front-end architecture. The back-end hosts all the services that have been developed in the IEMAP project, while the front-end is essentially the website from the user. The back-end is made by a service, mainly the REST API service, developed with the framework in Python called the Fast API, and this is deployed with the containerization using a Docker framework. This service is hosted on a VMware platform that allow to expose the services with the virtual machine, and Nginx is the reverse processing server that accepts the connection from the website and then forward to the services that are hosted in the Docker container. So the front end asks for any URL. This is accepted by Nginx and then forwarded to the real service. The REST API service essentially allow to interact with data that are permanently stored on a MongoDB database, while this database essentially stores the metadata related to the project, while files related to the project, the single project, are hosted on a file system, a remote and distributed file system called Chef, on servers located at Brimisi. This is the general architecture. If you have any question, you can interrupt whenever you want. Then a brief overview regarding the REST API. REST API stands for Representation Space Transfer. This is one of the modality architectures that allow to expose a resource to the external user with the application programming interface. The key concepts regarding this architecture are the resources that are hosted on the server. With the resources, I intend a web page, files, data on database, and so on. These resources are accessed with a URL or URI, Uniform Resource Identifier, and the client that in this type of architecture is called REST clients, invoke is the correct term used when the client programmatically and not through the web interface interact with the resources on the server, ask for a specific endpoint. The endpoint allows to expose a service. For example, access to data hosted on the database. The difference is, from the usual common website is that the URI accepts additional methods or webs like post, put, delete, and usually accept as a response a JSON format or eventually an XML, but more commonly a JSON format, and not a web page with formatted with HTML with the contents represented in as a web interface. As said before, some endpoints, hopefully the term endpoint should be now clear, are protected. Protected means that the user has to register on the website. From the main page, there is a button, sign up. Following that button, the user is redirected to this form where he can enter his institutional email address, can select one of the precompiled institution affiliation, and obviously type in a password with a minimum of 8 characters. This is the first step for sign up. After this first step, user is redirected to this page, and following to this redirection is sent from the web server to the registered email, an email with a link, this verifying your registration. Only after the user has verified the email by clicking on the button, the creation of the account is completed, and the user is redirected to this final page where it's stated that the user, by clicking this button here, can now on sign up and access all the protected endpoints. If the user does not click on the activation email, the account is only temporarily available on the host server. This means that the user can access, but the restricted endpoints are still restricted. So the functionality of the platform is not at its full. The user has to validate his account. Accounts that are not validated within 24 hours are automatically deleted from the host server. The creation of the project and the platform is done by filling in an Excel file. The Excel file is available on the platform, on the website. Is made up by some sheets named project, process, material, parameters, properties, and one additional sheet called how to. In the how to, you can find useful information on how to compile this Excel. The key point in compiling in filling in the Excel file is that the project has to be associated with only one process. Each project is associated with one process and only one. This means that I start here, I select a project, a label, and a description that is not necessary. You can fill in or not. And then you go to the process sheet, but here you can only include one process. While for material and parameters and properties, you have the opportunity to add many items. All of these items are in the form of a key and value and eventually a unit. These elements constitute what is the metadata for the project. This type of solution has been set as a type of form of compromise to allow all the users of the platform to interact and store on the platform the main elements and the main information about the project and the process that they are currently working. All data is additional data, for example, CSV file, text file, PDF, or so on, can later added to the project after having filling the metadata project and after having created the project. So the next step is to actually create the project. So the first step is to compile Excel file previously. Within this page, you have this button that allows to load the Excel file. This Excel file is converted on the client as JSON. This type of JSON is a visual feedback that the data have been correctly inputted, and this data, by clicking the create project, are actually sent to the back end and hosted on the database. This is so the first two steps allow to create a project with its metadata. Any additional data is to be inserted with this additional page at step 3, where the user is redirected after having successfully created the project. You can see here Add Files tab with a button that allows to select a file on the host computer to be uploaded to the backend. So uploading files is the next step, not necessary, it's facultative. You can select a file with this button I don't know, someone wants to ask something? No? Okay. With this interface, you can select the data, the file from your host computer. Here is a reported list of allowed files. Also, TXT data are allowed. The list is actually not really complete. I will fix this as soon as possible. You can also select the data, the file, then click to upload. After clicking upload, the real uploading starts. You will see a progress bar. After the being saved successfully on the back end, the file present a checkpoint indicating that the file has been successfully uploaded. After uploaded, you can here the project file see the yet uploaded file on the backend, and eventually download and check if everything is worked fine. The other part that is in this case publicly available, one note, what I illustrated before was available only to the registered users, while this page is publicly available. And this shows all the projects listed and currently saved on the platform. You can filter data from a material, so you can start typing the material formula, and according to this, if the elements in this list are filtered, you can also filter by date. These are the only two fields that can be used to filter the projects that have been shared on the platform. At least at the moment, I have in mind to upgrade this page to allow additional filters. What I've seen, then you can also click on view to have to view additional information about a specific project. What I described till now is related to the web interface or front end, and as you can see, you can interact with the front end without programming. The alternative way to interact with the platform is using a programming language. In previous webinar, I showed in detail how to interact. I here only briefly described the procedure. Essentially, I will develop the image available publicly on Docker Hub. By downloading this image and instantiating a container, Docker container from this image, you will have a platform, essentially a container that is accessible simply by a web browser. You will find a Jupyter notebook, and in this Jupyter notebook I reported a code example that show how to interact with the platform using the IEMAP pattern model publicly available on PyPy. Here you can also find the code that I have developed for this example in Python on GitHub. Obviously, you can also interact using the REST API interface also in other programming language. While if you use select Python as a language, you can specifically adopt the Python model that essentially is simplifying in some way how to interact with the platform. Here you can find also in the slide two brief video that illustrates how to install Docker in Windows or in Linux. The procedure should be quite simple. And this way you can, this is the second way to interact with the IEMAP platform. Essentially, with this way, I can save metadata regarding my project, my activities, all data that is not considered the metadata is shown before can be saved as additional files in the format that are available: PDF, CSV, TXT, Excel, and some other types. And this, okay, well, okay. This essentially concludes what has been developed so far. Now, only a few words about the task to complete. I'm currently working to add another functionality to the platform, and I will talk in more details in the second webinar during this day at about 4 p.m. This additional functionality is related to semantic search. Semantic search means that I can search the database not only by a specific word that I can find in the database in the same exact way, but with explaining essentially a concept. Here we have an example that sums what's the meaning of semantic search. If I ask the capital of France, obviously I have the correct answer. But if I ask what is the capital city of the country where the Eiffel Tower is located, a general system is not able to extract the meaning, the semantic meaning of this question. While with semantic search, I can, in the same way, have the correct answer twice, because it understands the relationship between Eiffel Tower, France, and its capital city. This type of functionality is essential. Briefly explain what's the meaning of semantic search, and it's one of the tasks that I'm currently work on, and hopefully it will be available on the platform for the end of this month. Another task to complete within the IEMAP project is to allow an easy access to some artificial intelligence model that have been developed by the colleagues. Essentially, a geometric information analysis crystal graph neural networks that allow to predict the properties of crystalline materials. Here you can find the details of the article. In this picture is illustrated the extract of the specific architecture of this type of neural network. The main idea is to allow to access with this functionality in different models. One way is to deploy a custom Jupyter notebook using Docker, in the same way that I've done previously for the yet developed model Python. Other option are to use the user interface, but to add an additional web page to allow to access this functionality within the web interface, or eventually with the REST API. Here I will listed some useful resources about the arguments I will briefly talk today. Obviously, you can find something useful. Here you can find my email if you have any other question. I can answer you if you want to. the presentation is ended. If you have any question.
Thank you very much, Sergio. Very interesting presentation with a lot of information and details about the technologies already implemented and and also those that will be implemented soon. I think that they are very challenging. The semantic search and also the machine learning tools available on the platform. That's great. I think
if you don't have any question, I stop sharing the screen, or someone is not clear.
I don't see any comment in the chat, and also is almost 10:15, so we can move to the next presentation. Thank you again, Sergio. Giovanni, the next
yes,
presenter from RSE, the other institution, research institution involved in the project. Thank you for being here, Giovanni, and the floor is yours. Give a short presentation of you and then the webinar. Thanks.
Okay, I share my screen.
Yeah.
Okay.
Yeah, okay, we see.
Good morning, everyone. My name is Giovanni Bagnale, and I am project manager in RSE, a public research company carrying out its activity into the field of electrical energy. And the activity covers the entire supply system with an application-oriented experimental system-based approach. So today we are going to talk about this presentation is divided into two parts. The first part, the presentation is focused on application development for the estimation of photovoltaic materials parameter. The second one deals with experimental trials done to reproduce the results of this simulation. Okay, aim of the activities to develop a new monolithic heterobiaxial structure in order to get one single junction photovoltaic cell for luminescence module suitable for building the integration. Replacing the gallium arsenide substrate by silicon substrate in the production of this kind of the device, and so to reduce the cost and environment impact. What we want finally, we want to turn the windows in module solar in order to produce energy. And we want to perform this putting all around the edge of the Windows solar cell. Okay, at the state so far, for the science device, the gallium substrate is more suitable. It's produced on gallium arsenide substrate because it's more suitable to producing the gallium phosphide solar cell for its property. For transferring this technology on a silicon, we have to take account different chemical physical property of 3-5 material respect to the silicon. This difference property produce plastic deformation, which generate defects in the grow layers. For this reason, we developed an application based on mathematical models able to select the materials, the compound position and the deposition sequence, for minimizing the generation and propagation of the defects. This one is the main challenge in order to integrate 3-5 materials on the silicon. This one is example for the plastic deformation interval system. So we developed a software application based on flow chart showing in this slide. And according to the flow, we can calculate several parameters of the epitaxial template simulated, solving this equation set code. And in this case, we see that the equation system is quite complicated to solve. In any case, we developed a function coding. This one is an example where it's possible to see some parameter information about the material and also information about the structure we can simulate using this application. Coded this software using an approach by object in order to be this application more friendly in the use for our application. Okay. This one is an example of the results using this application. In this case, we simulate the growth on the silicon substrate of helium gallium phosphate materials, changing the composition and changing the temperature range. And this slide shows and summarizes the results using the application and basing on the using the results basing on the results of the simulation, we designed and simulated indium gallium phosphide single junction solar cell grow on the silicon substrate. What we simulated is this one structure, the metamorphic structure, and is based on gallium phosphide nucleation, a helium gallium phosphide metamorphic layer, buffer layer, in order to match matching the silicon substrate with the helium gallium phosphide device. Basing on the results of this simulation, we performed also the growth of this structure using epitaxial reactor, MSCVD reactor. This slide summarizes the results using this equipment, and also it's possible to see the parameter using during the process. For example, temperature, composition of the layers, variation of the composition, and finally also the doping materials using for the active layers of the device. This one is just a brief characterization of the epitaxial structure. It's possible the structure will fully relax with respect to the substrate and the silicon, what is expected, of course, basing on the simulation. And the next slide, it's possible to see the TEM analysis showing a cluster of dislocation, especially in the location layer, and it's very close to the interface with the silicon. It is also the results of what we expected, and also with this one is the results we expected by the simulation performed. So using this approach, we finally we produce also a diode, and we perform also some electrical characterization. This is the device. For example, we report the EV device measurement. So in conclusion, we studied a different epitaxial process, simulated and developed with the aim to transfer one junction indium gallium phosphide solar cell technology for LC application from gallium arsenide substrate to silicon substrate. We did this one using a mathematical model coded for this aim, and finally we identified the indium gallium phosphide metamorphic buff layer, which allow to control the generation, the propagation of the defects in the active layers. IMS3D process grow, and the material grow was characterized. And also the first solar cell device was processed on the wafer growth. I conclude saying it's very important to this kinds of approach, and especially using this mathematical model and application coded just to because it's very important to reduce the number of trials, and of course it's very important to have tools able to simulate a different solution in terms of epitaxial process, because it is to help the research in the design of the device and also of the experimentals. Thank you. That's all for attention. Okay.
Thank you very much, Giovanni, for the nice presentation. I don't know if there are some questions or I don't see anything in the chat or no. And it's
Okay.
So okay.
Okay, I remove the share of this.
The software will the software be available some way?
Yes.
Do you have an idea on that?
Oh, no, the software is available. Of course, in this moment I coded in using the Visual Basic, and I'm working into coding the set of coding the software also in Python. But I needed times to do this one. But of course, the first version is possible to get disabled.
Okay. Okay, great. And also the data generated, I don't know, can be generated by the code, can be stored on the platform, IEMAP platform.
Yes, I have already done this one. In the platform, I put the data generated from the code for the software. For, of course, for the list of the materials we use for our process. But in any case, it's possible to update with other materials.
Yeah.
If it's necessary. In this moment, I generated a database of the materials we use in our equipment. Because in this moment we have able to produce, grow, and only specific compounds, 3-5 compounds. And so in this moment, I coded also for these kinds of the compounds. But if one has special requirement as possible to update the software in order to produce the same information, the same data for other compounds or materials someone wants.
Okay, great. That's interesting. Okay. Thank you again, Giovanni. The next presenter is in 15 minutes. It will be by Alessandra Alberti. So I don't know if it's convenient.
I'm
here. Yeah, I see. Thank you, Alessandra. I don't know if it is convenient to wait 15 minutes for a coffee, or we just start and then have a break later, as also is supposed to be in the agenda. I would start and then have a longer coffee break if okay, Alessandra, the floor is yours.
Can you see the screen?
Not yet.
There is a
Yeah.
delay. Okay,
Yeah.
so sorry for this
Perfect.
delay. Okay, good morning, everyone. It's a pleasure for me to be here to show you part of our laboratories at the Institute for Microelectronics and Microsystems of the National Research Council of Italy. And to show you how we exploit those laboratories for perovskites and the related material for third generation solar cells. To start with, I like to thank my colleagues, Giovanni Mannin, Emanuele Smecca, Yannis Derezis, and Pietro Pappalardo for working a lot on this project, which is Mission Innovation IEMAP. So we work in a wonderful place, which is called Etna Valley. It is close to the Etna Vulcan, and in the industrial area where we work, you can find big companies in the field of microelectronics, such as ST Microelectronics, but also ASM. And big companies in the field of photovoltaics, Enel Green Power and Trisun, who is building up a big factory, a gigafactory, as I think you know, for production of solar panels, in which perovskites are going to be integrated. So here a tour, at least virtually, in our labs, in some of our labs. You see on the left our clean room, which has been recently expanded to 300 square meters of surface. Inside or outside, you can find equipments for in vacuum deposition of materials, oxide, perovskites, and so on. On the right, you see a microscope, a transmission electron microscope, which goes to the sub-angstrom resolution, and many other laboratories for electrical, optical, structural characterization. Quite recently, I like to show you this project, which has been developed by CNR, so by us, in collaboration with some industrial providers. It is an equipment in which you can put inside a material or a device, and you can do simultaneously several kind of analysis. So you can have an output, so you can measure a current or a voltage, or for a solar device, you can do also maximum power point tracking. At the same time, you can shine on top X-rays or sun, or you can select a wavelength to shine on top of the device. And at the same time, you can do X-ray diffraction for analysis and photoluminescence as well for analytical purposes. You can also fix the temperature, if you like, from 10 to 90 degrees C. And also you can choose the environment for keeping the samples, or nitrogen, pure dry nitrogen, or air, or vacuum if you want. So it's the new frontier. Inoperando analysis are the new frontiers, analytical frontiers that we want to exploit in the project. So why we focus on perovskites and perovskite solar cells? Just a brief introduction. Perovskites are special materials in which many atoms are involved to set up the lattice architecture. It is an ionic lattice with anions, cations, and at the center you can find a species or an organic species. Methylammonium, formamidinium, or cesium are the ones mostly used. So you prepare the material and you integrate the material inside a device in which, as soon as you shine light, you create electron and holes couples that must be efficiently extracted by using electron transporting layer and transport layers. This is the basic principle. With this, you can get flexible devices. It is not easy to do that with commercial products. So a mainstay is like this, is the flexibility. And thanks to this property, the idea is integrating perovskite solar cells into in buildings, so for building integrated photovoltaics, in agrivoltaics, in greenhouses, for instance, or you can use also indoor because they are really well working indoor for powering devices in domotics. So a lot of applications. Perovskite solar cell have been initiated in the 2009, so quite recently. The first photoconversion efficiency was 3.5. After that, in just 10 years, the efficiency was impressively raised up to 24%. And currently, the certified record is of 26.7%. The technology was initiated by Professor Tsutomu Miyasaka at the Toei University of Yokohama. You see Toma Miyasaka with me in Yokohama. And Professor Miyasaka was visiting us in Catania and teaching and staying with us. The reason why worldwide there is really a huge interest for this technology is that this technology is competing with silicon, with single crystal silicon solar cells, and also with this 26.7% certified by NRL is very close to the results on silicon heterostructures. With this introduction in mind, we are going to see our laboratories for X-ray diffraction and spectroscopic. We apply within the project mission innovation to study the materials and mostly perovskites for low-cost approaches and low environmentally impact perovskite solar cells. As you see, the two techniques are similar in the sense that they are based on the interaction between radiation, let's say, and matter. In the case of spectroscopic ellipsometry, use a probe which span from infrared to ultraviolet violet light. In the case of X-ray diffraction, the probe is simply an X-ray source, monochromatic X-ray source. So here you see the laboratories. On the left, the one dedicated to the X-ray diffraction. On the right, the one dedicated to spectroscopic ellipsometry, but also you see a glow box and other stuffs to characterize the material in the devices, and also a view of our clean room in a part in which there are our equipments, two sputtering systems dedicated to oxides, transparent oxides to build up the architecture of the perovskite solar cells. And there is also in front of us an equipment, in vacuum equipment, for evaporation of perovskites. So why spectroscopic ellipsometry is so important in the field? It is simply because perovskites must collect solar light as much as possible. So it is important to evaluate the absorption coefficient of the material. Perovskites are direct in direct band gap, but they at the same time they are complementary in absorbing light. So for this reason, big companies in worldwide are integrating the two technology in tandem. I would like to show you an application of spectroscopic ellipsometry for the characterization of a kind of perovskite with a special formulation, which is cesium lead iodide, the one that can be used for tandem solar cells, but also for building integrated photovoltaics, thanks to the band gap it has. So now the issue is we don't want to have this transition. From a colored black phase, you see on the left is a brown color sample, toward the yellow phase, since the first one, the one on the left, is photoactive. The other one, the yellow one, is not photoactive. So a purpose is studying this transition for avoiding that it occurs. And to do that, we usually apply spectroscopic ellipsometry. And here you see how the real and imaginary part of the electric constant change with time during this transition. And you see the curves going from the brown to the yellow in a continuous way, meaning that the material is changing from photoactive to the one which is not photoactive. You see also the simulated lattice structure. The good one, let's say, as a lattice architecture which is well organized. On the other hand, when you turn to the yellow phase, the material is somehow is a puzzle of atoms, and it is not able to create, to generate charges inside. So it is photoinactive. So with this technique, we can also follow, so it's a quantitative technique to follow the amount of a phase with respect to the other phase. And you see during time, the yellow phase is growing whilst at the same time, the black phase or brown phase is reducing in a symmetric way. So they are competing one to each other. So keep in mind this, because at the end we propose a solution to avoid this transition once we know the mechanism. The other technique we want to talk about is diffraction. So why diffraction, X-ray diffraction is so important? Here a case you see in which a perovskite fingerprint is clear at the beginning, but during time and once we apply the temperature, there is a competition between the perovskite and the byproduct, which is the lead iodide PbI2. And during time, there is they flip one to each other and the color becomes yellow. So also in this case, you can follow the phase transition. And what is occurring inside the material is that the material is losing volatile species, and for that it is not as performing as at the beginning. Yes, we here apply the technique showed before in the case of explored within mission innovation within our project. And here you see some rings and the related diffraction pattern. By analyzing both together, we end up with disclosing the lattice structure of the material, which is an orthorhombic phase, which is photoactive. But as soon as you apply the temperature, you see the rings, the diffraction rings becomes a lot of, but apart from that, they are saying that the material, the lattice architecture is changed. So, and it is changed in another phase, which is still orthorhombic, but it is not photoactive anymore. And with the equipment and the system we have seen before, for in-operando characterization, simultaneously, we can explore the electrical response of the material, so the electrical output, and you see here the characterization of the device integrating the perovskite. So at the beginning, the device has a short circuit current of 13 milliamps per square centimeter, and an open circuit voltage of around 1 volt. But after applying the temperature, as soon as the material changes structure, the current flowing through the device is pretty lost, fully lost. The question now is how to block this transition from the black to the yellow phase in cesium lead iodide. So a method to apply is doing further lattice engineering. So add species inside the lattice structure. And so we're choosing to add bromide together with iodide to share the same lattice. And also we decide to add also europium in a little amount. So by doing this, one effect is changing the band gap. So we move it from 1.72 up to 1.84 EV of band gap, which is the threshold starting from which the material absorbs. So by doing this tuning of the band gap, one can better fit the requirement for building integrated photovoltaics, but also for indoor application, which is one of the purposes of our mission innovation project. At the same time, we can explore the lattice architecture, and we can see that europium has also an effect in reducing the unit cell volume for the benefit of the stability of the entire lattice architecture. So in the end, we integrated all those materials based on cesium inside a device, which has a particular structure, since it is HTL-free. So HTL is the layer devoted to the extraction of holes. And since it is expensive and it is also not stable, it affects the stability of the device, we decide to skip it. Instead, we use the carbon-based solar cell, which is cheap, enriched, and the formulation of perovskite enriched with europium and bromide. And in this way, we end up with a more stable reusable, which is not to be neglected. This is the flowchart we use to build up our perovskite solar cells, integrated cesium lead iodide with bromide and europium. We explored the efficiency, the photoconversion efficiency, so the power of capturing photons. And we concluded in the project that a certain amount of bromide is convenient to be integrated, and europium is convenient as well to get a trade-off between photoconversion efficiency and device durability. So in conclusion, why this architecture we use this so important and useful for the project mission innovation, it is because you can integrate this architecture into complete capacitor PSC device, in which PSC, that is the perovskite solar cell, capture photons from the environment or from outside, from the real sun, if you like. And the generated charge can be collected, can be saved by the capacitor, which is integrated together, one over the other. So I think it's all. I thank you for the attention. I thank the organizer and Massimo Cellino for the organization of this webinar. Thank you.
Thank you very much, Alessandra. Very nice slides, very clear. Thank you for this presentation. I see no questions in the chat, but I see Giovanni. Yeah.
Yes, a question for Alessandra. Alessandra, which is the average efficiency for the perovskite solar cell at the moment?
What do you mean for average efficiency? You mean the certified one is 26.7, and it is certified by the NRL in USA, which is the official. It's a way to certify and to compare different technologies onto each other. So 26.7, of course, in the laboratory scale. Not in the upscaled conditions.
Okay. Okay, thank you.
You're welcome.
Great, thanks, Alessandra and Giovanni. We have time for another question if you want. Otherwise, we can have the coffee break, but before, since we are quite a lot this morning, I would underline that IEMAP project. I share you the screen, is part of a cost action. Maybe, I don't know, maybe some of you already knows, but last year a cost action about material acceleration platforms started, and Where is it? Okay, I share all the screen. That's all. This is a cost action started last year. It is EU MACE. It means European Materials Acceleration Center for Energy. As you can see, some MAPs, Material Acceleration Platforms, are involved in this project. And the IEMAP is one of them. There is a big map, IEMAP, Diadem, EPSRSE from UK, Material Digital in Germany, Hyperlab, that is infrastructure project for PV. That's very interesting. Many institutions are involved all over Europe. And what is very interesting is that there are money fundings for traveling. So you can start a collaboration with other labs, and you are supported in these research activities with all the others project. The coordinator is Savako Nakame, shortly Sako. She's a CA in France. The project is divided in 3 pillars. Working group 1 is perovskite. Working group 2 is complex alloys. Working group 3 is for new materials. And then there are transversal activities. G1 is for maps, to increase the accessibility to maps like IEMAP. G2 is for communication and collaboration in this large network, so on and so forth. There are workshops, conferences, schools that are organized by the cost action and are paid by the cost action. So what you can do, and the idea is that, as you can see on the right, there are several labs that are connected to maps in Europe, and all together they work to involve industries and to provide tools, new technologies for the acceleration of discovery, acceleration of materials. I don't know how many institutions are already connected to this cost, because they are growing day by day. You can join the cost action by writing to SACO, and so you can start participating, and you will be part of this network. The project started last October, so almost 1 year ago, and it will last for 4 years. She's the coordinator, Sako, CA, Solid State Physics Department. And she's very motivated researchers. So, and also you can have, if you want to participate, please keep in touch with Monica Fabrizio, CNR. She is actually the vice chair for this. Is not more candidate. She's a vice chair for the cost action. So if you are interested, I can give you more information, or drop an email to Monica. So I think it's very important initiative. This is why we are doing also our presentation in English, because hopefully IEMAP will be disseminated, the activities of IEMAP will be disseminated in the cost action network, just to check if there are someone interested to collaborate, to be involved in the IEMAP activities. So that's all from my side. I think we have 15 minutes for a short break. Let's have a coffee break and see you at 11:45 with Palermo for the presentation about numerical modeling of PV-based energy systems. Okay, so thank you very much. I see you in 15 minutes. Bye.